I work at Lawrence Livermore National Lab. This is a lovely picture of the lab. I don't know if you can see my pointer. Oh, you can, that's exciting. This is the one most attractive view of our facility. So over here we have some lovely rolling hills. Sort of in the back over here is our supercomputer facility. We at one point had the fastest supercomputer in the world. Then I heard we were down to like third or fourth. I think our newest machine is going to put us back as having the fastest again, which I guess is exciting. This angle is taken from our director's office building. I guess I should be focusing more on this version of the camera. And it's looking out at where some of our heavy metals research goes on over there, and there's the National Ignition Facility over there, and I'll talk a little bit about what all these things are in a second, and I will also get back to math. So my talk is basically a pretty broad overview of who I am, what I do on my job, how I got there, and a little bit about the types of math that I use on the job. And hopefully this will be broadly accessible. I've never given this talk to a high school audience before. I have given it to an early college audience. So hopefully you'll think it's cool enough. Okay, yeah, so we'll start with my background. So I mentioned I identify myself as a mathematician. So I'm actually a Fremont native. So yay, I put that up there. I graduated from Washington High School in 1996. Fremont's pretty awesome hometown, at least I thought so. Back in 1996, it did look pretty different. So when I went to Washington, it had like almost no real buildings. It was mostly various portable trailers everywhere. Back in 1989, there was sort of a real school building, and it got condemned by the 1989 Loma Prieta earthquake. And then it took the school a while to actually get a new building rebuilt. I think it was 1998. Washington in its current form wound up opening. But so the time I was there, we didn't really have so much in the way of classrooms, but it was wonderful anyway. American high school at that time had no walls, so I thought I would point that out, at least no walls between classes. So it was very like a 1970s, like new age, like let's all learn in one room concept. So that was kind of interesting. I do have a degree in math. I got it from Pomona College back in the year 2000. I took loads of fun math courses while I was there. I took a good mix of applied math and pure math courses. So if you've never heard of pure math, it's math basically for the sake of math. It's a lot of theorems and proofs about things that you can prove are true. It doesn't have a lot of connection to the real world, and they pride themselves on not having a connection to the real world. So it's kind of unusual. And it's beautiful and fun, but yeah, it's not for the faint of heart. How about that? I did go, there's one really awesome college study abroad program in math. I think there's probably others you can do, but pretty much the penultimate one, at least when I was in college, is the Budapest Semesters in Math program. It is a pretty fantastic experience to go live in Eastern Europe and get to learn math with Hungarian mathematicians who are world renowned for their contributions to number theory and combinatorics and several other domains. And then you also can like bum around Europe on weekends. I mean, it was amazing. A lot of people, at least when they get to college in math, are interested in doing some sort of summer internship. I did one too. There weren't nearly as many opportunities when I was in college as there are now, but I spent 2 summers working at the National Security Agency, which is in Maryland, Fort Meade, so kind of between DC and Baltimore. And it's the world's largest employer of mathematicians. It was a wonderful summer experience. I can never talk about anything I actually did on the job, but suffice it to say, I had a very good time there. I got a PhD in operations research, which is a branch of applied math, and I talk about what that is, like in a couple of slides, back in 2006. And I've been at Lawrence Livermore ever since. So I guess I just passed 14 years there, which seems really hard for me to believe, but there it is. So operations research, I mentioned a couple slides ago, it is a discipline it's a branch of applied math, and it really focuses on how do we do things better? How do we solve things better? How do we optimize things? How do we answer questions for people about how to improve the state of the world? So that's kind of the thought of it. There are a few subfields of math that feed into this quite well. The first of these is optimization. So trying to figure out how can you take an algorithm or a sequence of steps to do things and do it more efficiently. So there's a lot of fundamental work that goes into taking algorithms and scaling them to run faster. You can also try to find better solutions, such as ones with improved cost. And I think I have one example later on in some of the work I've done in the optimization space. Simulations, another big one. So figuring out how do you model all the pieces of a system? How do you figure out how they all fit together? And then how can you actually make things go better by changing things around? And then probability and statistics is a big part of it too. I will fully admit that I am weaker in this area than probably I should be. It turns out MIT, though it's really awesome for a lot of things, really does not have much of a statistics department. So people assume that I'm much stronger in the stat and data science area than I am. But I'm reasonably good at probability and very good at optimization. In general, my field draws on ideas from math, computer science, business, and engineering. I think in general, people who had math backgrounds tend to flock to this kind of field the most and had the easiest time of it. Who actually employs people with my sort of background? So operations research is, as I mentioned, an applied math field, and there's a few sort of main sectors that look at it. So airlines hire a lot of operations research people. They typically have these really big optimization problems that we think of as discrete optimization problems. We say discrete because the kinds of decisions they're making have to be integers. So in their case, they often have decisions like, how many planes do we route between city A and city B on a given day, and what staff do we have assigned to those planes, and what crew do we have on there, and like meal services, all the other things they need to coordinate to satisfy demand in terms of passengers. And then the challenge for them is the planes are, you can't actually have fractional solutions to this problem. You're actually either flying between a place on a given day or you're not, and you can't really have like half a plane or half a pilot. And so it actually makes it very challenging to solve mathematically in an optimal fashion. So they have operations research people who work on that. Auto manufacturers do too. They'll typically try to understand their production lines really well. They'll simulate how they run. They'll try to figure out how to make things go faster if they move various parts of the line around. They're very into process optimization, which is pretty cool. Telecommunications companies are also a big customer for operations research. They'll have like these giant networks that they need to put together of cell phone towers, and they want to figure out, okay, so if we put the towers here, how much traffic will they actually encounter? And then they also want to know if one of the towers goes down, how can we reroute things so that people basically don't have an interruption in service? And that winds up being a really cool kind of optimization problem called network design. So they have operations research people too. And then OR is used at national laboratories like where I work in national security and other related domains. I'm guessing, since you're in high school, you probably haven't heard of national labs too much. I certainly hadn't when I was in high school. Oh, but I should mention, I actually did make up quite a few songs while I was in high school, so I really enjoyed the last talk. I thought it was really fun to sing about math, which probably should have been indicative of the kind of person I would eventually grow up to be. Anyway, Lawrence Livermore is one of 17 national labs run by the Department of Energy. There's a few Department of Defense labs out there too. They're typically not called national labs. So if you hear the term national lab, it's probably one of these. So this is my favorite graphic, by the way. The labs are kind of arrayed on this spectrum of like super pure sciencey oriented over to more like engineering and technology oriented on the right. And the larger sort of multi-purpose labs are on this outer ring, and the smaller single program labs are on the inner ring. And so some of these ones, like these single program labs, they'll just be like an accelerator where you go and run some experiments, and that'll be kind of their only focus. They'll typically be pretty small. Whereas these larger ones, like I think Sandia is probably the largest of the national labs. They have almost 14,000 employees. So, and everyone else kind of falls in the middle. I work at Lawrence Livermore, which is sort of a little bit more on the sciencey end of at least the National Nuclear Security Administration labs. Lawrence Livermore, Los Alamos, and Sandia, I believe, are the three largest of the national labs, although probably wouldn't quote me on that. They're all run by the National Nuclear Security Administration, which is a branch within the Department of Energy that does most of the classified work. That's probably a good way of, as good a way of ending is delineating that. We have about 7,000 employees on site. Our lab was founded about 70 years ago, and yeah, about 3,000 scientific staff, of which approximately half the folks have PhDs, at least among the sciences. And then in terms of occupations themselves, we have a lot of engineers, which some people find surprising, a fair number of physicists, and then a good deal of computer science people, of which I would say computer science is definitely predominant, because we have a supercomputing function and people who do basic supercomputing research and stuff. I'm currently misclassified as a physicist in our job code system, which I find hilarious. The lab's mission itself is to strengthen national security via use of science, technology, and engineering. There's 4 sort of main thrusts and then 3 sort of domain areas that go along with it. So the top one of these is stockpile stewardship. We are one of the design labs that make sure our nation's nuclear weapons are safe, secure, and perform how they're supposed to, when they're supposed to. Sandia and Los Alamos are the other 2. We have general work in weapons of mass destruction, threat reduction, a little bit of work in multi-domain deterrence, and then some, I say, the politically correct arm of the work in energy and climate security. And I've worked in all these areas except the WMD one. I haven't worked so much in that one, but I've certainly worked in the other 3. And then, yeah, the core competencies being science, engineering, computing. Now that all sounds very nice, but you kind of want to know, like, what actually makes where you work cool. So here's what actually makes us cool. So the claims to fame of Lawrence Livermore, there's really 3 of them. So we have the world's largest laser. It is in the National Ignition Facility. It's basically this giant field, stadium, like 3 football fields large. It's not actually a stadium, it has a roof. But it's 192 laser beams focused at a single point that generate an amount of combined fusion energy resembling that of a star. So it's very, very large. We also, this slide was probably actually a little bit outdated. For a while, had the world's 2nd fastest supercomputer, which is Sierra. I don't actually know that it's 2nd fastest anymore, but I do know we are re-getting the fastest one. So it's kind of a cyclic sort of thing. It's either our lab or Los Alamos, or I believe Oak Ridge. It tends to rotate between the 3 of us in the US, and then China also has a lot of fast supercomputers too. We do have an element on the periodic table named after us, element 116, livermorium. There's basic chemistry and heavy materials research that goes on at the lab too, which is cool. All right, so that's enough of like selling on where it is, my workplace. What it is that I actually do. So I've been at Lawrence Livermore for 14 years. I've had a variety of roles. Yes, I wrote my current job is the coolest. That is absolutely true. I have a really long title. Even though I call myself a mathematician, my actual title is Associate Program Leader for Nuclear Weapons Enterprise Evaluation and Planning, which is a really long title. I didn't make it up myself. But what we do is we try to answer questions along the lines of how do we make the National Nuclear Security Administration enterprise run better and faster, and the DoD enterprise too, sort of writ large on top of that, but especially the National Nuclear Security Administration enterprise. And we do it at varying levels of resolution, like down from like, how do we make our own lab run faster and more efficiently? And all the way up to like, how do we figure out how to position our country relative to other countries in the sorts of things that we care about. I mean, it can get very abstract sort of at the uppermost level of the scale down to very concrete, but I have a couple of examples of that coming up later in the talk. I am a manager. Sometimes people ask me like, oh, what's that like? Do you still get to do technical work, or do you just manage people all day long? Yeah, I mean, at our workplace, most managers, I wouldn't say they're not managers by choice, but most of them are technical people at heart. How about that? And so I'm a programmatic manager, not an administrative manager. I don't have to deal with performance appraisals or time cards or any of that like administrative overhead stuff. I get to do the fun stuff, which is leading the technical work side of things, which I enjoy a lot more. I'm right now managing a portfolio of maybe 10 projects or something, and there's about 8 people who work for me, and yeah, it's fun, and I like that I'm not in charge of the administrative side of things. We do have about $3 to $4 million. Yeah, that sounds about right. That we're in charge of, and I'm responsible for bringing in new work and for the technical output that the group produces. This is our beautiful slide of what it is we do. So we build mathematical models, in short, and I talk a little bit in a couple slides as to what I mean by that. But we try to study in the big picture in terms of the National Nuclear Security Administration enterprise. So at the very lowest level, we have things like workforce planning models that look specifically at how many people are working at a particular site and how do we think that's going to grow and change over time. So with respect to our own lab, we'll have models predicting, so there's one I was working on this summer that basically looks at where do we think our programs are going to be going in the future? How do we translate that into office space in which people are going to sit? And how can we actually get a hold on when people are going to retire and how to actually transition knowledge to the younger generation. We're pretty stoked as a lab to finally have our average age under 50. Yay! It was above there for quite some time. Now it's down to 48, so we're doing pretty well. But in general, getting in a younger workforce is kind of an important thing because a lot of the complex workforce was started around the Cold War and or during the Cold War, and they're all nearing retirement age now. And it's time to actually figure out how to transition what we do onto a younger generation. Incidentally, I count as one of the young people there. I like that I'm in a division where I think the average age is like still 55 or something where I am. I mean, it's crazy. The level up from the workforce models, we have individual site operational models. I'll talk a little bit more about one of these in a couple slides. So we look at things like how many experiments can we actually crank through our experimental facilities? Like what pieces of equipment and types of people would we need to have around to actually get more stuff done? So that's a fun one. There was another one I actually worked on relative to COVID this past, well, March, April. Which I thought you guys might find interesting. I'll just throw it out there to mention. We looked at how to bring people back to the site safely after COVID hit. So how can we bring people back to the office such that they don't sit too near each other and they're not going to be using a lot of the same sort of shared resources. The lab in general has been very, very cautious about how it brings people back, back on site. We do have a lot of classified work, so we can't do a lot of our work remotely, and there's some, but a large body of the weapons program can't work remotely. And so there was a lot of conscious thought given to how to bring people back safely so that they can do their jobs, which I think they handled extremely well. So we did mathematical algorithms for if you were to schedule people to come into work, how would you schedule them so that there wouldn't be too many people in at a given time, and then overlaid with maps of where people at the lab actually sit and who's coming in. So it was cool. Sort of above that, we have individual integrated stockpile models. So I do work on the nuclear weapons planning side of things. We look at things like strategic materials, supply and demand of what goes into nuclear weapons. I don't want to go into much more detail than that, but it can be pretty cool stuff, and it's definitely involves being able to talk not just to math people, but you have to be able to talk to physicists. You have to be able to talk to engineers. you have to understand kind of how things work and how to build them together into a mathematical framework that makes sense of it. We also have cost models, and then sort of the highest level nation scale deterrence type models. And I won't go into any details about what those are, but you can probably guess. We've been involved in this area, my particular group, for over 15 years. I guess it's probably closer to 20 years now. I've been in the group for almost 14 years, and it was probably about 4 years old when I started. So there's a number of popular publications that have been done about our group over time, and that's just a list of a few of them. Okay, let's get on to what I actually do a little bit. So I mentioned I do mathematical modeling, and this is my own graphic that I made up as to what is entailed in building a mathematical model. So we usually get approached by some sort of customer who has some sort of real world need. Like in the case of the COVID one, it was, how can we bring people back to the site so that they're not all going to infect each other? That's a pretty good real world need right there. But sometimes they're a little bit more nebulous than that. Our real world need we're looking at this summer was office space, and how can we actually accommodate the number of people who are coming back to the site, given how our programs are growing and where are they all going to sit? We're going to run out of room for them, was pretty much the conclusion. So they'll come with a need. The next thing you have to do, which is like 90% of the job, I feel like people don't, I definitely did not appreciate this when I was in college or even grad school, is collecting data is like the hardest, most annoying, most time-consuming part. But when you have the data, it's so awesome. So then you spend time trying to figure out, given their nebulous problem, how can you actually collect data to quantify it in some way, shape, or form? And I show one of the ways that we did this on an example on the next slide, which involves talking to subject matter experts. Other things I like doing is like mining financial data. Even if we don't have good records written down about a lot of things, we typically have finances that go back over time. So you can track those to get an idea of how things have changed. Yeah, I will just take any data from anywhere and try to use it to inform problems. You then make assumptions after you've collected the data to figure out, okay, how can I simplify this into something that actually makes sense that I can solve using math? Because usually that's like not super obvious. And you want to be able to simplify it so you can actually, get an actual solution, but not simplify it to the point that it's not actually meaningful to people. And then finally, once you've done all that, you could do what I think is the super fun stuff, which is you build the model and then you run it and you analyze the results. I love doing that. I love geeking out on data. I love geeking out on analysis. And then you ideally, well, if you're doing your job well, you go back and actually verify you're solving the need the customer had, and that usually they'll take some rounds of iteration where they'll be like, oh, that's not exactly what I had in mind, or that's not how that works, or what were you thinking there? And then you'll go back and you'll tweak things and run it again, and in the end produce a product that helps them make a decision. So one example I wanted to raise here of a math problem that we worked on is how can we increase the number of hydrodynamic tests that go on at our site? I don't think I have a definition of what a hydrodynamic test is here, but it's usually a test involving a large quantity of high explosives where you blow stuff up and you try to understand the physics behind what's going on in the explosion. So they're tests of fundamental physics, usually with other sorts of components, and you try to figure out how's the high explosive interacting with those other components, and what are the equations of state that go along with it. So basic physical properties. So to actually solve this problem, which is a very sort of open-ended stated problem, we decided, well, first let's figure out what the process is by which we do these tests. And so we sat down to actually define what it is. This is a lovely slide that actually, I didn't put it together, someone on my team did, that goes through the different steps in actually delivering one of these giant hydro tests. So there'll be a part, you can kind of see on the top, the part here in purple where it goes through manufacturing, and a part down here in orange where you'll actually have high explosives pressing and machining. So the purple stuff is actually at our lab's main campus, which is what we call Site 200. It's in Livermore. Incidentally, I live in Livermore these days. And then Site 300 is a lab's external offsite testing facility. I mean, it's technically part of the site, but it's 17 miles away. It's a It's in the hills between Livermore and Tracy. It came close to getting burned up by wildfires not too long ago, but fortunately it didn't, so that was good. It's where all of our large quantities of high explosives are tested and detonated, and like, yeah, because you don't really want to be doing that in the town of Livermore, not so much. Anyway, so we put together this map of where all the items in this process take place. On the other side of things, we have what you actually do. What do you actually do with the hydro tests? So some of these tests, we heat them up. Some of them we shake them, and some of them we blow them up. So the contained firing facility and the dual axis radiographic hydro test facility in Los Alamos are the chief places that we blow things up. So we tried to understand that. The next step was the most difficult part, I would say, yeah, is actually trying to collect the data. So we talked a lot to subject matter experts, and we had to define assumptions on what pieces of data we actually wanted to look at and how do we quantify them. And so this was our simple schematic of the manufacturing process of the hydro test. Each one of these little graphics represents a type of worker, and each one of these little cute things next to it represents a piece of equipment. So we had to get an idea of what people are working at each of these stages and on what pieces of equipment, and then these little numbers down here, and how long does it take them to actually do that job. And this is a super simplified schematic, but in general, there's two main lines. One that's manufacturing at our main site, another one that's building high explosives out at site 300, and then you assemble the device together and eventually explode it. We're in the process of adding a little more detail to the and then you explode it part right now. It involves other facilities that we don't have on here. Next, after you've done all that sort of hard work, data gathering and assumption gathering, you then actually get to do the math. So you get to build the model. In this case, this is my one slide of equations in this whole talk. In this case, we did a mixed integer linear optimization framework. I'm a operations research person by training, so this is kind of my bread and butter, but it looks kind of like that. I see we're running low on time, so I'm not going to dwell on it at all, but we use Pyomo, which is a Python-based algebraic modeling language, and we solve it with an optimization solver. So after that, you get the results. These are some beautiful results that one of my staff coded up in R. It's kind of a little bit hard to see what's going on here, but in general, we were looking at the kinds of people who are impacting our ability to get hydro tests done and the types of equipment. And we noticed that there's high explosives assembly technicians, actually, are the most constrained people resource, because for some reason it's hard to get people to want to like sit around assembling high explosives all day long. I don't know why. It takes an awful lot of training to actually be proficient at that job before people will let you do it, and you can never do it alone. So it's interesting niche career. And then on the equipment side, we noticed this piece of equipment, which is a large assembly machine. I don't know who named it the big bomb machine, but that's what they named it. We noticed that was the most constricted piece of equipment. So we said, we should probably buy another big bomb machine. And they did. So we just heard the second big bomb machine has gone into she just got certified for being in operation. So that's cool. All right, I think I'm almost done here. So in the end, you want to validate, do your results model reality? And so this involves more iterating with the people who asked you the question and some of the subject matter experts, but it's very important. And then finally, yeah, that's pretty much it. So in conclusion, national labs kind of fill a niche sort of between academia and industry. We look at problems that are really not researchy enough for academia, but definitely not profit driven enough for industry. So I think it's kind of a fun thing to work on. I wrote, expect your career to proceed in a nonlinear fashion. I had a graphic that originally in this talk, but it would have made it way too long about all the different twists and turns that my career has taken to get me here. But yeah, it's definitely don't expect your career to just be one like straight sailing line from here to there. Just be open to things that pop up, and that's kind of how I've gotten to where I am. And I've not always done things that were fun. I happen to really enjoy my job right now, but if you talked to me a few years ago, I was on a project that I hated. Sometimes you have to do things like that, and hopefully it leads you to a better place, and in my case it did. And then, yeah, the hardest part of building a model is getting data. And then I have one picture of me at work that's like probably 10 years old now. I do have a picture of me with the stealth bomber, so I've toured around the National Nuclear Security Administration and the DoD complex. And then a picture of me, the new moms group at the lab. I co-chair that group. I have 2 little boys who surprisingly have not interrupted this talk. And yeah, we try to create a supportive community for each other. Anyway, that's it. Thanks, guys.
Yeah, thank you for your presentation. It was really nice how you used operational research to make better decisions, and it's really cool to learn about that because I'm pretty sure it's a new topic for many people.
Yeah.
Now it's time for our Q&A session, so we'll be asking you some questions that students have.
Sure.
The first question is, how does national security tie in with math?
How does it? I mean, there's various national security applications that will ask themselves for mathematical solutions. Like a real obvious one right now is COVID. There's a lot of epidemiological modeling going on right now, and a lot of that has fundamentally at its heart math. So that's kind of an easy one. Other national security applications, gosh, there's just so many of them that math plays into. We looked at, some of the other work I've done at the lab involved counterterrorism and trying to figure out how do you optimally allocate resources to guard against bad guys doing bad things that you don't want them to, given that you have a limited budget to actually spend on countermeasures. So that's another area. Math plays a role in homeland security. They're also more generally energy and climate security. There's a big role for math in there too. A lot of the energy grid problems wind up being very mathematical in nature. So I worked on one where we were trying to figure out how to actually port some commercial energy grid software to run on supercomputers so it would run faster. That's cool.
Oh, yeah, that's really cool how you can use your resources to like prevent like from bad people from doing things and making better decisions. Yeah, that's really cool.
Thanks.
And another question is like, how can students or high school students get internships or opportunities in mathematics or anything related to national security?
Yeah, it's a little bit tricky at the high school level. We definitely have quite a few people at the college level that we see, not really too many at the high school level at all. So say be open to whatever electives and alternatives that are out there that are mathematical in flavor, but it's not, I don't have a super obvious answer. There are various math competitions out there that the last speaker mentioned that I actually think are a good thing. But yeah, go to college and take a bunch of math classes would be my recommendation, and then a lot more opportunities wind up becoming available.
Yeah, definitely taking math classes in high school will help you get a better job in mathematics for sure.
Yep.
Someone was asking, what's a large-scale project you have worked on which we might have heard of?
You might have heard of. Well, I can mention the energy grid one. I don't know if you heard about California moving to a 33% renewable portfolio standard by the year, I think it was 2020. So yeah, by 2020, California wants to transition to having 33% of its power come from renewable power sources. And so I worked on how do we take the codes they were using to determine basically how are they going to plan for the future and how are they going to realize getting 33% renewables, and how to scale those codes so they would actually run faster so you could look at different renewable scenarios. I also worked on, that was the politically correct answer, also worked on the 80 Mod 4 Life Extension Program, which is a nuclear weapons refurbishment program that our lab is the lead physics lab on, and lots of other labs in the enterprise are. Sometimes Congress gets interested in it, but it's a cruise missile, and I worked on that one too.
Oh, okay. Yeah, that sounds like a cool project. I think it was heard of, and like it looks like a really cool lab that you have worked on. Yeah.
Thanks.
And another question were like, do you have any tips like what are some colleges or universities that you know of that have good applied mathematics programs for high
Gosh,
school?
I think a lot of them do, honestly. Um, yeah, I would say it's less about where you attend undergrad if you want to go into math, and more about where you attend grad school. So you want to go to an undergrad that you can get the level of experience and exposure necessary to get into a decent graduate program. I definitely would think math is one of those fields. It's not super easy to get a cool degree, a cool
Mm.
career with just a bachelor's degree. You don't need a PhD. A master's degree would probably be sufficient. But most of whom we hire, it's master's degrees and above. Um, you could probably get some sort of grunty data-ish work type jobs with a bachelor's, but it's, yeah, I think master's degree is kind of where it's at and starting. So go to anywhere that actually was a decent, that will actually, I mean, I would actually recommend going to somewhere that's going to pay attention to you and actually make sure you learn things and not, I mean, I loved MIT. It was a great place. It's kind of a rough place to be an undergrad. I don't know that I would have wanted to be an undergrad there. There wasn't a lot of attention paid to them, certainly by the professors. The stress level was really super high. A lot of kids were just taking way too many classes because there was an upper limit on how many you could take. It was kind of a pressure cooker. I went to Pomona College, which at the time was not as highly ranked as it is now, but it was a much sort of more intimate environment where the professors cared about us, and that worked out a lot better for me than going to a really big school. So somewhere that will allow you to shine so you can get somewhere better. How about that?
Okay, yeah, that sounds like a good idea. Like taking undergrad or like pretty much any college that has a good mathematical degree is very useful.
Yeah.
And someone was wondering, like, is your career similar to data science or is it kind of different from data science as
So I would say mine is different from data science. We certainly have a lot of data scientists at my workplace, though, so I don't want to say we don't do data science. We definitely do. Uh, Data science usually assumes there's this giant body of data that you're mining to actually get answers from. The problems I tend to solve are usually the ones where it's like, where's the data? How are you going to come up with anything to even quantify that? And then typically when you do come up with the data, there's hardly any of it. And so you have to be real creative to figure out how to draw conclusions from it. So that's, I like to say I'm more of a small data person because that's the kinds of problems I wind up solving. They tend to be problems that it's not real obvious where the data is coming from or how you're going to use it. And there definitely aren't mountains of it to actually sift through. So in that respect, I am jealous of the big data people.
well? Okay. Yeah, so I think we kind of got an idea of like the data part of the career, and yeah, that sounds cool for that part.
Yeah.
Um, and another question was, like, how does it feel like working in a national lab? Like, is it similar to working into like in other research labs, or is it like a different type of experience?
Depends on what you mean by other research labs. So it'll be similar to other Department of Defense research labs, especially ones that do classified work. There's various rules about what you can and can't do. Recently, we were actually allowed to have smartphones in our offices, which I found really, I guess I'm a bit of a Luddite. I refuse to bring my smartphone in, but then they banned them again. I was like, ha, yes, I was right all along. So there are a certain amount of precautions that you take when working in a classified environment. It's kind of similar, more in flavor, I guess, to how academia operates. It's kind of, except it's a lot more collaborative than academia. So I guess it has that part of industry. There's a lot of people who kind of congregate together in various offices. I'm really lucky that my team basically sits in a wing of a building, so I can say, "Ooh, I own my own wing of a building," but we just all happen to sit there. Yeah, it's a nice environment. Definitely, we definitely aren't in one of those pressure cooker things like what you would see in industry in a big wall of cubicles and everyone all hammering away together. We actually have our nice own private offices for the most part, and we can shut the door on each other if we want to. There's a lot of introverts who work there. They're a big fan of that. Yeah, it's a good place.
Yeah, it's really nice how like even in like national offices like the ones you're working in, it's like a private space and you it's like a normal lab, but it's also different in its ways of like being private, and yeah, that's
Yeah,
really nice of it. Hmm.
that made people coming back to work from COVID way easier. The fact that we have private offices because we
Hmm.
can just shut the door and not have to talk to each other. So I'm up to like one in-person meeting a week now, and that's it. And I haven't. That's all I'm gonna do. I don't want to talk to people in person. It's all
Hmm.
good.
Yeah. Thank you so much for your time and like for your amazing presentation, because it's a new topic that a lot of people, I'm pretty sure, learned about. And yeah, thank you so much for all these guests for attending our session today.
Thanks a lot, guys. Hope that was useful, informative, and/or fun.
Thank you.